Hey everyone, and welcome back to the channel. Today we're diving into something that's a huge part of modern technology, the electromagnet. This thing powers everything from giant industrial cranes to life-saving medical gear. But its real power? Well, it comes from a surprisingly simple idea.
But before we get into all that, let me ask you a question. We all know what magnets do, right? They stick to your fridge, they have a north and a south pole. Pretty basic stuff. But have you ever stopped to think, could you just turn a magnet off?
Well, the answer is a very simple and totally revolutionary yes.
And that simple yes brings us to this incredible concept, the on-demand magnet. This isn't just some cool party trick. It's a capability that has completely changed how industries work. I mean, just picture a huge scrapyard. You've got this giant crane, it lowers a big metal disc, and bam, tons of scrap metal just leap up and stick to it. The crane swings it all over, and then, just as fast, the magnetic force is gone. The metal drops exactly where it needs to be. That right there is on-demand magnetism in action.
So how in the world is that possible? How can we create and then destroy a crazy powerful magnetic field with just the flip of a switch? Well, the secret is all about the deep connection between electricity and magnetism.
You see, an electromagnet is, at its heart, just a temporary magnet. Its power only exists when an electric current is flowing. You turn off the current, you turn off the magnet. It's really that simple. It's not like that permanent magnet on your refrigerator. Its power is totally conditional.
And you only need 3 things to build one. Seriously, just 3. You need a coil of wire, you need an electric current to run through that wire, and you need a magnetic core, usually some soft iron, to really focus the power. Okay, now take a look at this diagram because it really shows you the magic. When you pass a current, that's the I you see there, through that coiled wire, which is called a solenoid, a magnetic field just appears. And you can see how the lines of force get super concentrated inside the coil. This creates a really clear north and south pole, just like you'd find on any old bar magnet. And here's a cool trick. We can actually predict which end becomes the North Pole. It's called the right-hand grip rule. Just imagine grabbing the coil with your right hand, so your fingers curl in the same direction as the current. Wherever your thumb is pointing, that's your North Pole. It's a super handy way to figure out the field's direction.
But just turning it on and off is one thing. The real power comes from being able to fine-tune its strength. So the next logical question is, how do we make an electromagnet stronger or weaker?
Well, it really just boils down to 3 key things. First, how much current you're pumping through it. More current means a stronger field. Second, the number of turns in that coil. The more loops you have, the more you amplify the magnetic effect. And third, the kind of material you use for the core. Now don't worry, I'm not going to make you do any math here, but this equation just perfectly illustrates the point. The magnetic field strength, that's B, goes up if you increase N, the number of turns, or I, the current. You boost either of those and your magnet gets stronger. Simple as that. That core material is also a huge deal. Soft iron is absolutely perfect for electromagnets because it gets super magnetic when you turn the current on, but it loses that magnetism almost instantly when you turn it off. Steel, on the other hand, likes to hold on to its magnetism, which makes it great for permanent magnets, but pretty useless for a magnet you need to switch on and off. Okay, so now that we know how they work, let's look at how this amazing concept actually gets used in the world around us. Because this controllable force is literally everywhere, from the simplest gadgets in your house to the most advanced medical tech out there.
So let's start with the classic electric doorbell. When you push the button, you're closing a circuit. An electromagnet flicks on and pulls a tiny metal hammer to hit the bell. But that very same movement breaks the circuit, which turns the magnet off, so a spring yanks the hammer back. This whole thing happens over and over again, incredibly fast, and that's what creates that familiar ringing sound.
And it just scales up from there. Electromagnets are the beating heart of pretty much every electric motor, turning electricity into motion in your fan or washing machine. We've already talked about the cranes. They also work as tiny automated switches called relays that control all the complex circuits inside countless devices. And then you get to the really high-tech end of the scale with things like MRI machines. These things use unbelievably powerful superconducting electromagnets to create magnetic fields strong enough to actually map the tissues inside the human body, giving us those incredibly detailed images that doctors use for diagnosis. So, as we start to wrap this up, let's just circle all the way back to the single most important idea. What is it that truly defines the electromagnet?
This quote right here really just nails it. The key advantage is one word: Control. It's the ability to change the magnetic field, to crank its strength up or down, to turn it on and off in the blink of an eye.
So, here's the real takeaway. The true genius of the electromagnet isn't just that it's a magnet. It's that it's the perfect bridge between electrical energy and a magnetic force that we can precisely control. It's a tool that literally lets us command one of the fundamental forces of nature.
This power is already fundamental to our world, in everything from tiny switches to massive particle accelerators. And that leaves us with a pretty exciting question. As we get better and better at using this technology, what new challenges will we command this controllable force to solve next? Thanks for learning with us today, and don't forget to subscribe.